Hey class, welcome back. Week 3, same thing, a bunch of questions to test your knowledge. This is where things get pretty fun. We're going to review things like tidal volume, gas diffusion, the oxygen hemoglobin dissociation curve, the Bohr effect, and my personal favorite, although I hate when it happens in terms of the burn, lactate threshold.
All right, welcome to week 3 review. So let's get started. A lot to review there in lecture 5 and lecture 6, another awesome week. So here we go, you know the format. What refers to an increase in pulmonary ventilation that exceeds the needs of oxygen needs of metabolism. And yeah, that's hyperventilation. This is lecture 5 after all. The what refers to the air volume remaining in the lungs even after exhaling as much as you can. Hopefully you guys figured this out. This should be the, yes, residual volume or residual lung volume. Some people just abbreviate it RV. Minute ventilation is breathing rate multiplied by, and that one is your tidal volume. Yes. FVC equals TV plus IRV, and what else? And if you think about this, this is then an all-important measurement. What are we missing? Yes, the expiratory reserve volume. Next one. So this is another one that we didn't really review, but hopefully you can kind of figure it out and it makes a little more sense now. So you see a lot of athletes bend forward from the waist to facilitate breathing because it promotes blood flow back to the what and minimizes the antagonistic effects of what on the usual upward direction of inspiratory movements or upward direction of blood. It's the heart and gravity. So you've probably seen when athletes are gassed and really heaving for air, they stand, bend forward, put their hands on their knees, and they're just breathing heavier because it's easier. You get a little bit more negative pressure in the thorax there, which pulls blood in a little bit more. If you bend forward, you can kind of help get rid of gravity just a little bit more. All right, approximately what percent of carbon dioxide is free in the plasma as opposed to bound to carboamino compounds or converted as bicarbonate? And this one is important. 5%, right? 20% is carbamino, 60 to 80 is bicarbonate. Is totally different from hemoglobin, which is pretty much 99% bound by oxygen. All right, two factors that govern the rate of gas diffusion into a fluid, right? It's the pressure, right? The pressure differential between the gas and the what of the gas. If you recall this is the solubility, yes. And that's the difference. CO2 is very, very soluble, much more than oxygen, if you recall. All right, mass of a gas dissolved in a fluid at a given temperature is in direct proportion to the pressure, right? The pressure differential of the gas over the liquid, provided no chemical reaction takes place. That is known as Henry's law. Yes, and we're not going to totally quiz you on specifically Henry's law, but it's a good one to review. If you remember this, you're going to really know what you're talking about. Another one here, another law or another effect. The interaction between oxygen loading and carbon dioxide release, termed the what, facilitates carbon dioxide removal in the lung. And yeah, that's the Haldane effect. All right, in humans, pressure difference between what and what blood gases create the driving force for gas across the pulmonary membrane. And that is simply the alveolar and capillary blood gases. Next one, blood carries oxygen dissolved in the what of blood and in loose combination with what? And that's going to be fluid and then hemoglobin. Only a little bit dissolved in the blood itself, or plasma. Those terms are often interchangeable. It's mostly with hemoglobin. All right, the what indicates that hydrogen ions and carbon dioxide altering hemoglobin's molecular structure to decrease its oxygen binding affinity. So what are we talking about here? What effect is this one? The Bohr effect, not the Haldane effect. All right, blood carries carbon dioxide in solution as what, combined with what, and as what? So what are the three ways carbon dioxide is carried in the blood? And hopefully you guys know this by now. This is just free carbon dioxide, carboamino compounds, which do include a little bit of hemoglobin. That's maybe surprising. And then as bicarbonate. All right, what curve illustrates the saturation of oxygen at various pressure levels? And that is simply the oxyhemoglobin dissociation curve. Right, myoglobin has a slightly different curve than hemoglobin. Because an active muscle's uncompromising capacity to utilize whatever oxygen is available in its large blood flow, the supply of what limits exercise capacity rather than the extraction or utilization, and that's oxygen. So we learn that it's not the lungs, it's not the ability of the lungs to pull in oxygen, it's not the content of the oxygen in the blood, it's not the extraction of oxygen of blood. It's the delivery, right, by the heart. It's the heart that's pumping that limits our VO2 max. All right, the VE, ventilatory equivalent, right, can attain values as high as what of air per liter of oxygen? So if you recall that VE goes down as we're exercising and then suddenly changes direction and goes up as high as 30, 35, even 40 liters, if you recall from that graph. And it's a sneaky question, yes, I'm sorry, but if you have been reviewing really closely, this really helps you learn the material. These questions are a little harder than what you get on the multiple choice by design. All right, the term what describes the highest oxygen consumption or exercise intensity achieved with less than 1 millimole per liter increase in blood lactate concentration above resting pre-exercise level. That's your lactate threshold, sure. And once the lactate threshold goes above 1, we know we're starting to get into trouble. Peripheral what protects an organism against reduced oxygen pressure? And those are your chemoreceptors. They're checking to make sure that we maintain adequate oxygenation. And it's mainly doing that by carbon dioxide and H+, but the goal is to get more oxygen. All right, neurogenic factors for ventilator control include what and what, and this is kind of a read your mind question, but it's very simply, bluntly, central and peripheral. Right? There's two pieces to that. There's the brainstem that controls stuff, and then there's those chemoreceptors and things like that we just talked about. In fact, we're going to talk about a few more coming up. The what describes the point at which pulmonary ventilation increases disproportionately, right, with oxygen consumption during exercise. So this is not the lactate threshold, this is the ventilatory threshold. And we now know that those are occurring at exactly the same time because they are interrelated. All right, next one. Blood lactate accumulation is reflected by plasma changes in what? Bicarbonate and H+ concentrations and what? Production via buffering. So if you think about this, lactate, right, accumulation is, we can see what's happening to lactate by knowing what happens to the pH, what happens to the bicarbonate and H+ concentration, and carbon dioxide production via buffering, via that equation that we talked about. All right, exercise intensity at the point of what consistently and powerfully predicts endurance exercise performance. So this is not VO2 max, this is your lactate threshold. This is your onset of blood lactate accumulation. This is your ventilatory threshold. Those terms are all describing the same point, or the exercise intensity, which is why it's such a good number to know. Exercise training generally reduces the what in submaximal exercise, which, so to speak, conserves oxygen during a specific exercise. And this is your ventilatory equivalent, yes. All right, variations in arterial O2, CO2, and what two other factors activate neural units in the brainstem and arterial system to adjust ventilation and maintain blood chemistry within very narrow limits, maintain that pH. And this is what? So it's the O2, it's the CO2, it's the pH, and it's the temperature. And hopefully that makes sense by now. All right, ventilatory response to exercise occurs in how many phases? Hopefully this is an easy answer. Well, it's 3, right? We kind of learned that from that curve. At ventilatory threshold, excess ventilation comes directly from carbon dioxide's release from the buffering of, and yes, that is simply lactic acid. Yes. All right, 3 indicators of lactate threshold include fixed blood lactate concentration, the blood lactate exercise, VO2 max response, and what else? What is another indicator of lactate threshold? And yeah, that's the ventilatory threshold. It's the whole point of what we're talking about in these lectures. This is why it's so much easier to measure lactate without using blood. All right, besides VO2 max, what other factor influences exercise performance in a specific exercise mode? And that is the maximum level of steady state or steady rate exercise at a tolerable level, and that's your lactate threshold. That's the highest level that you can maintain steady rate exercise. Besides chemical buffers and kidney function, what other mechanism regulates the pH of your internal environment in your blood, basically? Well, that's pulmonary ventilation, of course. That's how we get rid of that excess CO2 and maintain a neutral pH. All right, moving into the cardiac world here. Assuming a systolic of 120 and a diastolic of 80, the average, right, the mean force, all right, mean arterial pressure here is going to be what? And you'll have to calculate that. And hopefully, if you remember that equation, you'll calculate it pretty quickly. If you wanted to just kind of estimate it, it's about 2/3 of diastolic and 1/3 of systolic, because that's how much time we spend in each of those phases, and we get 93. As cardiac output increases during exercise, resistance to peripheral blood flow, what? During exercise Well, it decreases. That's vasodilation. And this should really be aerobic exercise, is what we're talking about here in terms of cardiac output increasing. With resistance exercise, your cardiac output doesn't really increase. All right, what body exercise produces higher blood pressures at a given percentage of oxygen consumption? And that is going to be upper. Yeah, so we're not as efficient at exercising. It's harder for our body to exercise. We get more pressure changes during exercise. Upper body in general is not as good when we're talking about pressure and VO2. All right, diastolic blood pressure, right? What does that indicate? It's a 3-word answer here, and that is your total peripheral resistance, right? That's what happens. That's your residual blood pressure after the heart contracts or beats in the system. One factor that triggers relaxation of those sphincters right in front of the capillaries there to open more capillaries is the local what produced during exercise. And it's a whole bunch of them there, but nitric oxide is a key one that we want you to know. If you remember that slide, there's a whole bunch of these relaxing factors that play into capillaries opening. What term describes moderate exercise done in recovery that facilitates blood flow, right? This is your cool down, right? It's opposite from the warm up. It's kind of a little review from the prior lectures, but it's trying to help stimulate that blood flow that we're talking about in our cardiovascular lecture. All right, heart pumps about how many milliliters for each contraction? Now, this might seem like, what? We don't know that answer, but actually, yeah, you do. What are we talking about in this sentence? Well, this is the stroke volume, so it's about 70, yeah, at rest for an average person there. During aerobic exercise, right, TPR, total peripheral resistance, is decreased by what process in muscles that are active, right? It's vasodilation, right? So when we exercise, sympathetics get stimulated, so that certainly contributes to vasoconstriction, but that's mainly in non-active muscles and organs that don't really need to be used during active exercise, which get vasoconstricted, but active muscles get vasodilation. All right, stimulation of sympathetic, so to speak, cardio accelerator nerves, terminating in the adrenal glands, releases the what epinephrine and norepinephrine. Again, sort of an intro into the next lecture, but what are epinephrine and norepinephrine? They are starts with a C, catecholamines, yes. The cardiac impulse starts at SA node, then goes through the what, then to the AV node and Purkinje fibers, which you didn't really review, and then ends depolarizing the what. This is simply the atria and the ventricles. That's the order of contraction. A little harder question, sorry, but that's the whole point of these, to really get you to review the material and identify little holes and gaps here. All right, the what effect causes the heart's contractility to increase. That's inotropic effect, right? This is not the speed or the rate of firing. This is the strength of the contraction, and that's the inotropic effect. Magnitude of heart rate acceleration relates directly to physical activity. What properties of physical activity? And this is stuff that we reviewed in the first few lectures. And this is simply exercise intensity and exercise duration. But now we know what it does in terms of heart. It certainly accelerates things up. All right, baroreceptors inhibits what outflow from the cardiovascular center to stop or blunt or limit an unnecessary rise in blood pressure. Right, it's the sympathetic outflow. These are the brakes, right? They say, whoa, what's going on? Your blood pressure's going up way too high. We don't want you to have a stroke. We're going to slow things down a little bit until your body kind of gets used to it and says, oh, okay, we're exercising, and it readjusts and resets at a higher steady state to allow a little bit higher blood pressure. All right, an increased what nervous system outflow and local chemicals that directly stimulate what contribute to reduced blood flow to non-active tissues. And that's the sympathetics, what we just talked about before. So sympathetic nervous system cranks up and says, let's vasoconstrict areas we don't need. This is our fight or flight time. We need to promote blood flow to the areas that we need. Neat way your body adapts. All right, what 2 types of receptors does muscle contain that monitor, and this is the hint here, its chemical state and physical state, those 2 states, and those should make sense now. Chemical state is going to be, right, yes, chemoreceptors. Physical state or mechanical state is going to be, mechanical receptors. Those are the 2 ways that muscles communicate to the heart, chemoreceptor, and to the lungs, to the pulmonary system. All right, epinephrine and norepinephrine are 2 types of what group of hormones? Catecholamines, yes, an intro to the endocrine system that we're going to be reviewing soon. Sympathetic nerves terminate in the medullary portion of what gland? Another intro to what's to come, the adrenal gland. During graded exercise, what does not plateau in transplant patients? So yeah, a little bit harder question here, but if you recall, there's two kind of types of responses here to exercise in terms of heart rate. And what's different in transplant patients? Well, if the stroke volume can still go up, the heart rate response is certainly blunted because you don't have the sympathetics anymore in transplant patients. So yeah, the heart rate tends to reach a plateau in exercise, whereas stroke volume continues to slowly go up and up. And that's mainly because those catecholamines that we talked about released from the adrenals will eventually make it to the heart and slowly cause the contractility to increase. All right, the what law of the heart, or principle, not necessarily a law, associates increased end diastolic volumes with increased contractions? And then it's yes, the Frank-Starling principle or Frank-Starling law. All right, typical resting cardiac output is about what? Right, most people say it is 5. Some people say it's maybe 5 for some men, maybe 4 for some women, but in general, 5 is the understood answer. All right, Fick equation expresses a relationship among cardiac output, oxygen consumption, and what? What's that third part of that Fick equation when we're measuring cardiac output? Yes, it's the AVO2 difference. Okay, I was able to figure that out. Pretty impressive stuff. All right, this one's a little bit harder. This was actually coming from the Show Me whiteboard session there, because it's from a different textbook. Upon reaching a plateau in stroke volume at about half of your VO2 max, which does happen if you're in a relatively untrained state or even a decently trained state, cardiac output can only increase by increasing what? And if you review that Show Me, you'd know this. This is going to be the heart rate. So it's kind of an interesting thing that we don't really have too much time to get into, but it's believed in some older studies that when you start measuring both the heart rate increase and stroke volume increase in exercise, if you are untrained, your stroke volume goes up, goes up, goes up, goes up as you're exercising. But once you get about 50% of your max, it kind of reaches its limit. And then the only way for you to further increase cardiac output is you increase your heart rate. In decently trained, so to speak, athletes, they did another study and it seemed to show that as well. But actually, these studies were done back in the 70s, I believe, and they found that when you test elite athletes, they actually are able to continue to increase their stroke volume all the way through, and it doesn't necessarily plateau at 50%. Real interesting topic to go into. I encourage you to review that. Show Me. All right. Some of the factors that contribute to a large stroke volume and low heart rate of endurance athletes are increased watch tone and increased myocardial what? So you got to kind of think about that to get that answer. But what's going on? Are they just cranking on sympathetics all the time and just got the pedal to the metal and fight or flight at all times? No, they got a low heart rate because they have an increased parasympathetic or vagal tone. That's the vagus nerve, and increased myocardial contractility. They don't need to pump as hard because their body knows that their stroke volume gets stronger. So they say, all right, we don't need to have our sympathetics firing as much. All right, another kind of hard one. We did go over this in the lecture, but 5 to 6 liter increase in blood flow accompanies each what liter increase in O2 consumption when you're exercising, so above resting value. And that's a linear relationship, and it's 1. So about 5 liters of blood flow to 1 liter of oxygen is what we see, and that's how cardiac output is very linear and directly relates to oxygen consumption. That's how we learned that cardiac output is what limits oxygen consumption, or VO2 max. All right, during resting conditions, another hard one. If you're looking at that pie chart, what gets the highest percentage in terms of organs of the body at rest? It's an important one. It's your liver. Just had to give you a little hard one in there, sorry. All right, what term describes an increased resistance to blood flow in the arterial system from exercise-induced elevation of systolic blood pressure? And that is going to be your afterload. Another hard one, we didn't really talk about that, but if you recall the preload of the heart, right, when more blood comes through the venous system and enters the heart, stretches out the heart, and then you get a better contractility via Frank-Starling. That's your preload. There is an afterload too, and that's the increased resistance when you're starting to exercise more with resistance exercise, and you get higher mechanical pressure. That's your afterload. That's what your heart has to pump against. So there's preload and afterload. All right, way to go.